According to the National Electrical Code, the grounding conductor for a spa circuit must be insulated or bare copper and must be installed in accordance with Article 250.130. This means that the grounding conductor must be protected from physical damage throughout its entire length. The circuit from the interior service to the ground fault circuit interrupter protected disconnect, if it's mounted within 5 feet of the spot, also needs to have an insulated ground conductor, even within the crawl space. If the circuit from the interior service to the ground fault circuit interrupter protected disconnect is installed in a crawl space, it is a location where the grounding conductor is likely to be exposed to physical damage. Therefore, the grounding conductor must be insulated to protect it from damage. The only exception to this rule is if the grounding conductor is installed in a raceway. If it is not installed in a raceway, it is best to assume that the grounding conductor must be insulated. Article 250 provides comprehensive requirements for grounding and bonding electrical systems to ensure safety. Grounding and bonding are essential for minimizing electrical shock hazards and ensuring the proper operation of overcurrent protective devices. Within Article 250.130, specific requirements are outlined for the type and installation of grounding conductors for various applications. Section 250.130 addresses equipment grounding and bonding requirements. It details the methods for ensuring a low impedance path to ground for metal enclosures and equipment. This low impedance path is crucial for facilitating the operation of overcurrent protective devices such as circuit breakers and fuses in the event of a ground fault. The low impedance path allows sufficient current to flow during a ground fault, causing the overcurrent device to trip and disconnect the circuit, thereby minimizing the risk of electrical shock. Section 250.130 covers grounding electrode conductor connections. This section specifies the acceptable methods for connecting the grounding electrode conductor to the grounding electrode system. The connection must be mechanically secure and provide a permanent, low-impedance path to ground. Acceptable methods include exothermic welding, listed pressure connectors, listed clamps, and other approved means. The grounding electrode system typically consists of one or more grounding electrodes such as ground rod, metal underground water pipes, or concrete encased electrodes. Section 250.130b addresses bonding of metal enclosures and equipment. This section requires that all metal enclosures and equipment likely to become energized be bonded together into the grounding system. Bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of voltage differences that could create shock hazards. Acceptable bonding methods include bonding jumpers, listed bonding fittings, and other approved means. The size of the bonding jumper must be sufficient to carry the available fault current, as specified in Table 250.102 Cone. Section 250.130c covers grounding of separately derived systems. Separately derived systems, such as generators and transformers, require their own grounding electrode system. This section specifies the requirements for establishing a grounding electrode system for separately derived systems, including the size and type of grounding electrode conductor and the location of the grounding electrode. The grounding electrode conductor must be connected to a grounding electrode, such as a ground rod or a metal underground water pipe, and must be sized in accordance with Table 250.66. Section 250.130d addresses grounding of equipment on or in buildings. This section provides requirements for grounding equipment that is located on or in buildings, including the use of equipment grounding conductors and the bonding of metal enclosures. The equipment grounding conductor must be installed with the circuit conductors and must be sized in accordance with Table 250.122. Metal enclosures must be bonded to the equipment grounding conductor to ensure a low impedance path to ground. In the specific case of a spa circuit, additional requirements apply to ensure safety in and around the spa. These requirements are outlined in Article 680 of the National Electrical Code, which covers swimming pools, fountains, and similar installations. Section 680.26 specifically addresses bonding requirements for spas and hot tubs. This section requires that all metal parts within 5 feet of the spar be bonded together to create an equipotential bonding grid. This includes metal piping, metal structural components, and electrical equipment. The purpose of the equipotential bonding grid is to minimize voltage gradients in the area around the spar, reducing the risk of electrical shock. The bonding grid must be connected to the equipment grounding conductor of the spar circuit. In addition to bonding requirements, ground fault circuit interrupter protection is also required for spar circuits. Ground fault circuit interrupters are designed to detect small leakage currents to ground and to quickly disconnect the circuit, preventing electrical shock. Section 680.42 requires that all 120 volts and 240 volts spar circuits be protected by a ground fault circuit interrupter. The ground fault circuit interrupter must be located in a readily accessible location, such as at the service panel or at a disconnect switch near the spar. The ground fault circuit interrupter provides additional protection against electrical shock in the event of a ground fault. Furthermore, the National Electrical Code provides guidelines on the sizing of conductors for spar circuits. The conductor size must be adequate to carry the maximum load of the spar, as well as any additional loads that may be connected to the circuit. The conductor size must also be selected to minimize voltage drop, ensuring that the spar operates sufficiently and reliably. Table 310.15b16 in the NEC provides ampacity ratings for various conductor sizes and insulation types. The ampacity of the conductor must be equal to or greater than the calculated load of the spar circuit. In addition to conductor sizing, the National Electrical Code also provides requirements for overcurrent protection of spar circuits. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect the circuit from overloads and short circuits. The overcurrent protection device must be sized to protect the conductors in the circuit, as well as the spar equipment. The overcurrent protection device must not exceed the ampacity of the conductors or the rating of the spar equipment. The National Electrical Code also addresses the installation of underground wiring for spar circuits. Underground wiring must be installed in accordance with Article 300 of the National Electrical Code, which covers wiring methods and materials. Underground wiring must be protected from physical damage by being installed in a conduit or direct buried cable. The depth of burial must comply with the requirements of Table 300.5, which specifies the minimum burial depth for various wiring methods and voltage levels. The National Electrical Code also provides requirements for the location of spar equipment. Spar equipment, such as pumps and heaters, must be located in a readily accessible location and must be protected from physical damage. The equipment must also be installed in accordance with the manufacturer's instructions. The location of the equipment must also comply with the clearance requirements of Article 110 of the National Electrical Code, which covers general requirements for electrical installations. Article 110 provides requirements for working space around electrical equipment, as well as for access and egress. Adequate working space must be provided around the spar equipment to allow for safe maintenance and repair. The access and egress to the equipment must also be clear and unobstructed. In addition to the requirements of the National Electrical Code, local codes and regulations may also apply to spar installations. Local codes may have additional requirements for grounding, bonding, and ground fault circuit interrupter protection. It is important to check with the local electrical inspector to determine the specific requirements that apply to spar installations in your area. Following the requirements of the National Electrical Code and local codes ensures that spar installations are safe and compliant with applicable regulations. Proper grounding, bonding, and ground fault circuit interrupter protection are essential for minimizing the risk of electrical shock in and around spars. Regular inspections and maintenance of spar electrical systems are also important for ensuring continued safety and reliability. The installation of an insulated grounding conductor in the crawl space for a spar circuit is a critical safety measure. The insulation provides protection against physical damage, reducing the risk of ground faults and electrical shock hazards. By adhering to the requirements of the National Electrical Code and local codes, the electrical safety of spar installations can be significantly enhanced. The grounding conductor, whether insulated or bare copper, plays a vital role in providing a low-impedance path for fault currents, allowing overcurrent protective devices to quickly disconnect the circuit in the event of a ground fault. This rapid disconnection minimizes the duration of exposure to hazardous voltage, reducing the risk of electrical shock. The installation of a ground fault circuit interrupter is another essential safety measure for SPA circuits. Ground fault circuit interrupters are designed to detect small leakage currents to ground and to quickly disconnect the circuit, preventing electrical shock. The ground fault circuit interrupter provides additional protection against electrical shock in the event of a ground fault, even if the grounding conductor is not properly installed or maintained. Proper bonding of metal parts within 5 feet of the SPA is also critical for minimizing voltage gradients in the area around the SPA. Bonding ensures that all metal parts are at the same electrical potential, reducing the risk of voltage differences that could create shock hazards. The equipotential bonding grid must be connected to the equipment grounding conductor of the SPA circuit to provide a low-impedance path to ground. The combination of grounding, bonding, and ground fault circuit interrupter protection provides a comprehensive approach to electrical safety for SPA installations. Regular inspections and maintenance of SPA electrical systems are also important for ensuring continued safety and reliability. Inspections should include a visual examination of the grounding conductor, bonding connections, and ground fault circuit interrupter. The ground fault circuit interrupter should be tested periodically to ensure that it is functioning properly. Any damaged or corroded component should be replaced promptly. Maintenance should also include cleaning the SPA equipment and ensuring that all connections are tight and secure. Following a regular maintenance schedule helps to prevent electrical problems and ensures that the SPA operates safely and reliably. In summary, the installation of an insulated grounding conductor in the crawl space for a SPA circuit is a necessary safety measure to protect against physical damage and reduce the risk of electrical shock. According to the National Electrical Code, the grounding conductor must be insulated or bare copper and must be installed in accordance with Article 250.130. In addition to the grounding conductor, proper bonding and ground fault circuit interrupter protection are also essential for ensuring the electrical safety of SPA installations. Regular inspections and maintenance of SPA electrical systems are also important for continued safety and reliability. By following these guidelines, the risk of electrical shock in and around SPAs can be minimized.